Assalamu alaikum dear students, I hope you all are fine and in the best conditions of your health. So for the course of organic reaction mechanism, today we shall discuss about the selectivity in organic synthesis. The key concepts of this lecture will include the selectivity, then we shall see about the specificity, and then we will see about the type of selectivity. Right, so firstly about the selectivity. Selectivity means preference, right? So when we say about the selectivity in organic synthesis, it means that when we are carrying out a reaction with a reagent, the reagent prefers one substrate to another, or the reagent may prefer to attack on one position over another. For example, if you have two substrates available and a reagent is preferentially attacking one substrate over the other, right? It doesn't mean that the reagent is not attacking on both substrates. It means that the reagent is attacking on both substrates, but the reagent is preferentially attacking one substrate, resulting in formation of one product in more amount and the other product in a lesser amount. The other way around, selectivity may also involve the preference reaction of a reagent on one position rather than other position, right? So in simple terms, for example, that if you have a substrate available, it has two positions which can be attacked, right? But if one of the position is sterically hindered, then your reagent will not attack on that hindered position, right? So your reagent is preferring the position which is less hindered. So this is called selectivity, right? So selectivity is the preference which is shown by the reagent, right, when it shows preference either over one of the two substrate, or it shows preference over one or more of the two positions which are available, right? The selectivity is broadly divided into three categories: chemoselectivity, regioselectivity, and the stereoselectivity. So chemoselectivity is actually focused on the functional group, right? So whenever you see about the term of chemoselectivity, it should come in mind that you are talking about the functional group. So what do we mean by chemoselectivity? Chemoselectivity means that you have two or more functional groups available and your reagent is preferring one of the functional group, right? So it means which of the two functional groups will react. Right, so chemoselectivity is about the preference of the reagent for a particular functional group. Right, so chemoselectivity means which of the two functional groups available will react. Regioselectivity is dependent on the position. It means that if you have more than one site available for a reaction, then which of the position or where your reagent will react, right? So regioselectivity is related to the term of where, and what we mean, it means that on which position or where your reagent will attack, right? So the regioselectivity is related to the position or the site of action. Third term of selectivity is the stereoselectivity. The stereoselectivity is related to the stereoisomer. It means that which of the stereoisomer will react, or in which three-dimensional space the reagent will react, right? So if you have two stereoisomers, then stereoselectivity will determine that which of the two stereoisomers will react. Also, the stereoselectivity is focused on that how the stereoisomer will react, right? It's not only dependent on which of the two stereoisomer will react, it will also depend on how the stereoisomer will react, right? So we have three types of selectivity: the chemoselectivity, which is related to the function group, and chemoselectivity is the selectivity or preference of one of the functional group to preferentially react. Regioselectivity is dependent on the position or the site of action. So regioselectivity actually explains that which of the two positions will preferentially react. Stereoselectivity is related to the stereoisomer. It means that which of the two stereoisomers will preferentially react, and it also explains that how the stereoisomer will react, right? So firstly, we shall study about the chemoselectivity, and we will see different examples of chemoselectivity in order to make this concept much clearer, right? So chemoselectivity is the ability of the reagent as well as intermediate to react with a functional group in a molecule in preference to functional group present in other molecule, right? So if you have two functional groups present, then the preference of the reagent or the ability of the reagent to react with one functional group in preference to another. Or we may also say that if there is a reaction intermediate, then the preference of the intermediate to react with one functional group to another. So chemoselectivity is about the reagent as well as intermediate, but broadly we say it's the ability of the intermediate to preferentially react with one functional group over another, right? So chemoselectivity can occur when there are two different functional groups of unequal reactivity, right? So since there are two functional groups of unequal reactivity, then definitely the reagent will prefer the functional group which is more reactive, right? So the preference will result in chemoselectivity. The second case in which chemoselectivity can occur is that when there are two identical functional groups, right? So there will be preference when the preference of the reagent when two identical functional groups are present, then the preference will be on the basis of static effects or on the basis of electronic effects. So we shall see about the different examples in which there is selectivity when the two functional groups are identical. The third possibility is that the reaction of the group can occur twice, right? But we want to react it only once, right? So when there is a functional group that can react twice. For example, if you have a primary amine, you know that primary amine can undergo double alkylation because this primary amine has two hydrogens which can be replaced. But you want to replace only one of the hydrogens, right? So you want the functional group to react only once. However, it may react twice, right? So these are the three cases in which chemoselectivity occur, right? The first case is that when you have two different functional groups and both the functional groups have unequal reactivity, so the reagent will prefer the functional group which is more reactive. The second situation is that when you have two identical functional groups, so the selectivity will be dependent on the static effects as well as electronic effects. Third possibility is that when you have a functional group which can react twice but you want to react it only once, right? We will see different examples of chemoselectivity now. So for example, we have selective reduction. So this is example when you have two different functional groups and your reagent will prefer one functional group over another, right? So in this specific case, we have two functional groups, that is a carbonyl group and a carbon-carbon double bond, right? So both of these groups are unsaturated. It means both of these groups can be reduced, right? But here the reagent, which is hydrogen over palladium, so this reagent prefers the reduction of carbon-carbon double bond, right? So this reagent also reduces this carbonyl group, but the reduction of the carbonyl group will not be preferred, right? So we will get two products in which a carbon-carbon double bond is reduced like this one, and other product in which the carbon-oxygen double bond is reduced. But the product in which the carbon-oxygen double bond is reduced, in which we will get a suppose the product which we will get will be an alcohol, right? So we will get a 5-member ring with an alcohol, right? And the double bond will be retained, right? So this reagent can carry out both type of reductions. So it can reduce this carbon-oxygen double bond, it can also reduce carbon-carbon double bond, but this product will be major. So this reagent is preferring the reduction of carbon-carbon double bonds. This is example of the reactivity when two functional groups are different. Another example, so the same substrate, but now we want to reduce this carbon-oxygen double bond and we do not want to reduce this carbon-carbon double bond. So in this case, we will use sodium borohydride. Why sodium borohydride in presence of ferric chloride? Because sodium borohydride prefers to reduce this functional group over that functional group, right? Again, we have another example. So here we have two functional groups, you can see. So a carbonyl group and another carbonyl group, but you can see that this carbonyl group is conjugated. So this is an alpha beta unsaturated system and this is a simple carbonyl system, right? So these two carbonyls are different, they are not the same. This is the alpha beta unsaturated system and this is a simple carbonyl system, right? So in case if you want to reduce this functional group, right, which is alpha beta unsaturated system, then you can use sodium borohydride, so, right? So sodium borohydride preferentially reduces the carbonyl group which is conjugated, right? So it can also reduce this carbonyl group, but the product in which this carbonyl group is reduced will be minor, right? So this reagent has preference to reduce this alpha beta unsaturated carbonyl group. This is the selectivity. Okay, this is selectivity in cases when the two functional groups are different. So you should not consider these functional group as same, right? So this is alpha beta unsaturated system and this is a simple carbonyl system. So both have reactivity which is different from each other. Another example here, this is also example of selective reduction. So here we have an alpha beta unsaturated system, right? So we have a carbonyl group and a carbon carbon double bond. So in case if you are interested to reduce this carbon, if you are interested to reduce this carbonyl which is isolated. Okay, so this is our reactant molecule. You can see here we have two types of carbonyl system. So one of the carbonyl system is alpha beta unsaturated and one is isolated simple carbonyl system, right? So if you are interested to reduce this isolated carbonyl system, then you should go for sodium borohydride, right? The sodium borohydride, in case if you used alone, this sodium borohydride can reduce this carbonyl to alcohol. But in case if you are interested in reducing this alpha beta unsaturated carbonyl compound, right? So in case if you are wanting to convert this carbonyl compound into alcohol, then you should better use sodium borohydride in presence of ferric chloride, or you can write it as 1/3 BH3, right? So if you are using sodium borohydride in presence of ferric chloride, then you will preferentially reduce this alpha beta unsaturated carbonyl compound. And if you are using this sodium borohydride in a lesser amount or in simple in absence of ferric chloride, then you will reduce this carbonyl compound which is isolated. Again, we have an example of selective reduction, right? So here we have an alpha beta unsaturated system and we have an alkene, right? So here we have a carbon carbon double bond which is part of an enone system, and here we have a carbon carbon double bond which is of an alkene. So we want to reduce only alkene and we do not want to disturb this carbon carbon double bond of the enone, right? For this purpose we use hydrogen over this rhodium tetraphenyl phosphine reagent, right? So this rhodium catalyst in presence of hydrogen, so this catalyst prefers to reduce this carbon carbon double bond which is not the part of the enone system, right? So this is the selectivity when we have two same functional groups present. So here we have carbon carbon double bond and also we have a carbon carbon double bond, but this carbon carbon double bond which is of simple alkene is preferred by using this reagent, right? Again we have this system again, and now we are preferring to use the enone over alkene, right? Then we have to use this reagent which is K selectride, solvent is THF, or instead we may use of this cupric methyl or methyl cuprate in presence of dibol, right? So this dibol reagent that will selectively carry out the reduction of the enonic double bond, right? So if you are preferring to reduce this enonic double bond, you have the preference either to use the potassium selectride or you may use this methyl cuprate in presence of dibol, right? So both of these reagents can work when you are considering the reduction of this enonic double bond. Now we have two different functional groups, right? So we have a carbon-carbon double bond and a carbon-carbon triple bond. So this is a situation when the two functional groups are different and we are preferring to reduce this triple bond here, right? So we don't want to reduce this double bond, we are just wanting to reduce this triple bond, right? So when you are preferring to reduce a triple bond, then in that case we have to use hydrogen over poisoned palladium, right? So if you use hydrogen over palladium, then all of the double bond or triple bond will be reduced to a single bond. But since we are preferring the reduction of a triple bond to double bond and we don't want to reduce this double bond, then we have to make use of poisoned palladium. So this is a poisoned catalyst and this palladium has been poisoned by calcium carbonate, right? So hydrogen over poisoned palladium will result in reduction of this triple bond in preference to reduction of the double bond here, right? Another example, so here we have a triple bond and a double bond, right? So system is open, previously the system was cyclic, and here again you can see that this poison palladium is preferring the reduction of this a triple bond. One important thing which is shown here is that the hydrogen over palladium always reduces the triple bond to result in formation of a cis alkene, right? So hydrogen over palladium always results in formation of cis alkene. It never results in formation of a trans alkene, right? So this is an important thing you should know, right? Again, chemoselectivity, in this case we have two different functional groups. So one functional group is an ester, and other functional group is a nitrile group, right? So this CN bond is called nitrile. So both of these functional groups can be reduced. So ester can be reduced to alcohol, nitrile can be reduced into methylamine group or methylene amino group, CH2NH2, right? So here we are preferring to reduce only ester group, and we do not want to affect the cyano group or the nitrile group, right? So for reduction of ester to alcohol preferentially, what we use calcium borate, right? So the solvent is methanol because the boranes are more soluble in methanol, right? So when you use calcium borate, then in that case you can selectively reduce the ester group into the alcohol, while the cyano group will not be reacted. Now we have again an example of two different functional groups here, two same functional groups. So here we have carbon-carbon double bond, again we have carbon-carbon double bond, but you can see that this carbon-carbon double bond is a part of alpha-beta unsaturated system. So this is alpha-beta unsaturated ester, right? And you want to reduce the double bond of the enone system, while you don't want to affect this alpha-beta, this isolated carbon-carbon double bond, right? So in order to reduce this double bond, which is part of enonic system, so previously you use sodium borohydride in presence of ferric chloride, but when you are using the alpha-beta unsaturated ester, you can use sodium borohydride in presence of the ferric chloride, but the preferred reagent will be to use magnesium in presence of methanol, right? So when you use magnesium in presence of methanol, then we carry out the selective reduction of this carbon-carbon double bond of the enone system, while the isolated carbon-carbon double bond will remain unaffected. Now we have chemoselective reduction of a carbonyl, which is part of aldehyde or ketone, and a carbonyl of ester, right? So here we have carbonyl, again we have carbonyl, but this is carbonyl of a ketone, and here we have carbonyl of ester. And we are preferring to reduce the carbonyl of the ketone. The best reagent will be to use sodium borohydride, right? So when we use sodium borohydride, we get this carbonyl converted into alcohol, while the carbonyl of the ester remains the same, right? So in case if you have again two type of carbonyls, a carbonyl of a ketone and a carbonyl of carboxylic acid, and you want to convert this carbonyl into a CH2 group, right? So use Clemmensen reduction, or also you can use the Wolff-Kirchner reduction. So both of these will result in the conversion of this carbonyl into CH2. So we are not preferring Wolff-Kirchner reduction here. The reason is that Wolff-Kirchner reduction makes use of basic conditions. So here we have a carboxylic acid group. So carboxylic acid group, since it is acidic, it reacts with alkaline conditions, right? So it is affected under basic conditions. So we will not use the Wolff-Kirchner reduction. Instead we will use the Clemmensen reduction, because Clemmensen reduction makes use of acidic conditions. So this carbonyl will be reduced, while the carboxylic acid group will remain unaffected. Again, now we have the chemoselective reduction of carboxylic acid, right? So in presence of an ester, or in presence of a nitrile group, or in presence of a cyano group, right? So if you have an ester, nitro group or cyano group in presence of carboxylic acid, and if you want to preferentially reduce only carboxylic acid, right, then what we use BH2 in presence of dimethyl sulfide, solvent is DHF, right? So under these conditions, this is cyclic ester. The ester will remain unaffected, right? So this BH3, so it's not BH2, this is BH3. So this BH3 will result in reduction of this carboxylic acid into alcohol, while the ester will remain the same. It is important to use dimethyl sulfide with BH3 under these conditions, right? So this reagent will preferentially reduce carboxylic acid, but it will not affect the ester group. Now we have two functional groups, both are carbonyl. So we have an ester group and we have an amide group, right? And we want to reduce the amide, the carbonyl of this amide group, and we do not want to affect this ester, right? So under these conditions, what we use BH3, right? You can see we are not using dimethyl sulfide, we are just using BH3, right? So BH3 in presence of THF, so this reagent can effectively reduce the carbonyl of the amide to CH2 group. Here you can see the ester remains the same. So this reagent is preferring to reduce this functional group over that. So this is chemoselectivity, right? Right, so next we have the example. So far we have considered the selective reduction. Now we are considering the selective oxidation process, right? So here we have selective oxidation of allyl alcohols over other alcohols, right? So this is an allyl alcohol. You know that if a group is directly attached with a carbon-carbon double bond, right? So if we have a hydroxyl here, then this group will be called vinyl, right? So this hydroxyl would have been vinyl if there were hydroxy here, right? But this CH2, which is directly attached with this carbon-carbon double bond, so this CH2 is called allyl group, right? This is allyl. So this CH2 is allyl group, right? And any alcohol which is attached to the allyl group, this is called allylic alcohol or allylic alcohol, right? So if you are considering the oxidation of this allylic alcohol, you can see that there is another alcohol here as well. So this is a simple alcohol, but you want to oxidize on the allyl alcohol, then you have studied about the reagent of magnesium oxide. So manganese oxide can only oxidize the allyl alcohol. So manganese dioxide does not oxidize the other alcohol. So this is a selective method in which we can oxidize only the allyl alcohol, and this simple alcohol will remain as such, right? Again, we have these two alcohols. So both of the alcohols are isolated alcohols, they are not allylic or vinylic alcohols, but you can see that one of the alcohols is primary while the other is secondary, right? And what we are wanting, we want to oxidize the secondary alcohol. We want to oxidize this alcohol to a ketone, and we do not want to affect this alcohol, right? So for this purpose, the reagent which is best is silver carbonate in presence of salide, right? So silver carbonate in presence of salide, that reduces this, that oxidizes the secondary alcohols, while the primary alcohol will remain as such. While in case if you want to preferentially oxidize the primary alcohol, then in that case the reagent which is this which is known as bleach, right? So this is sodium oxychloride. Sodium oxychloride is a common bleach, right? So but if you want to preferentially oxidize the primary alcohol, then you can use you can also use this reagent which is sodium oxychloride, right? Sodium oxychloride also selectively reduces the secondary alcohol, but it does not affect the primary alcohols. Now we have selective oxidation. Again, we have two types of alcohols. So both of these alcohols are primary alcohols, right? But this alcohol is part of this lactone ring. This part is of ether, right? This is present alpha to an ether group, right? So this is a lactol, right? So if just for your extra information, so if you have a cyclic ester, right? So if it were a carbon oxygen double bond, then it is called lactone, right? The cyclic esters are known as lactone, but this is not cyclic ester, it is just a reduced form of ester, right? So if there were a carbonyl group, we say it as lactone, but since it is not a carbonyl group, it's an alcohol, so that's why this functional group is called lactol, right? So we have two hydroxyl group, one is simple alcohol while other is lactol, and you want to oxidize the lactol, right? So if you want to oxidize lactol, then the reagent is silver carbonate in presence of salide. So this reagent will not affect any other functional group, it will just oxidize this lactol hydroxyl group. Now we have selective oxidation of two carbon-carbon double bonds. Here we have carbon-carbon double bond, again carbon-carbon double bond, but here you can see this carbon-carbon double bond is a part of allyl alcohol, right? So here you can see a carbon-carbon double bond, next to it is CH2, and we have a hydroxyl group here, right? So this carbon-carbon double bond is a part of allyl alcohol, right? While this is not any part of any such functional group. So if you want to preferentially oxidize carbon-carbon double bond, which is part of allyl alcohol, then the reagent is, we use this tertiary butoxide peroxide, right? And hydrogen tertiary butoxide, this is hydrogen tertiary butoxide, and we use vanadium diacetate, vanadium oxide diacetate, right? So this is vanadium oxide diacetate because this is acetate group. Two acetate groups are attached with the vanadium oxide group, right? So this reagent can oxidize this carbon-carbon double bond, which is part of this allylic alcohol. Again, the chemoselective epoxidation or the chemoselective oxidation. So here we have two type of carbon-carbon double bonds. So one carbon-carbon double bond is part of alpha-beta unsaturated system, while the other double bond is a simple alkene. And we prefer to oxidize this carbon-carbon double bond of the alpha-beta unsaturated system, right? The reagent should be potassium hydroxide in presence of hydrogen peroxide, right? So this reagent will preferentially epoxidize this carbon-carbon double bond here. But if you want to oxidize, or if you want to epoxidize this alkene, which is a simple alkene in that case, but in case if you want to just oxidize or epoxidize this simple alkene, then what you use metachloroperbenzoic acid. So this is simply called MCPBA. So MCPBA stands for metachloroperbenzoic acid. So in presence of dichloromethane as a solvent, so this reactions works well, and you can just epoxidize a simple alkene in preference to the alkene or the double bond of alpha-beta unsaturated system, right? Again, we have chemoselectivity, and here we are considering the chemoselectivity of acylation reaction, right? So this functional group in which we have a carbonyl group and an R group right here. So this group is called acyl, right? This group is called acyl, but in case if you have a methyl in presence of R group, this is called acetyl group, right? So in case if you have a methyl here, this is called acetyl group. Otherwise, overall in general, this group is called acyl group, right? So in case if you are considering the acylation, so here we have NH2 and OH, and both groups can be acylated, right? You can have an acyl group here and you can have acyl group here, but in case if you are preferring to have acyl group on nitrogen, then we say this is N acylation. And if you prefer the acylation on the oxygen, we say it is O acylation, right? So in this specific reaction, we are preferring N acylation. We want to have an acyl group on the nitrogen. For this reagent, so the reagent should be, you have to use acetic anhydride in presence of pyridine, right? So with this reagent, you can preferentially carry out the acylation of nitrogen, while the hydroxyl will not be affected to much extent. While in case if you want to carry out the O acylation, right, you want to carry out the alkylation, you want to carry out the alkylation of an OH. Now in this specific reaction, you have an OH of a carboxylic acid and you have an OH of phenol, right? But you want to carry out the alkylation of the phenol, and you don't want to carry out the alkylation of this carboxylic acid. For that purpose, you can use any base, because it's easy to pick up the proton of this phenol, right? So this base will pick up both protons, but since the phenoxide is more reactive, now when you carry out reaction with this iodocyclohexane, then in that case this negative charge of the phenoxide, right, so this negative charge will attack on the carbon bearing iodine, and iodine will be displaced right here, right? So since this phenoxide is the strongest nucleophile in comparison with this carboxylate group, so that's why it will preferentially react and will be alkylated, but the carboxylic group will remain unaffected. right? So in this way we can have the selectivity because the phenoxide is more reactive as compared to carboxylic acid group. Again, we have an example of chemoselectivity, and here the example is about the reaction of two identical functional groups, right? So we have two functional groups, both are alcohols, and you can see both are primary alcohols, but we want to react only one alcohol, but we don't want to react the second alcohol as well, right? So this is an example in which a molecule can react twice, but we want to react it only once, right? So in that case, the reagent should be used is sodium hydride in presence of benzyl bromide, right? So this reagent will prefer only this one of the hydroxyl groups, while the other will not be affected. So it's also important to use the concentration wisely. So if you carry out the reaction by making use of greater amount of sodium hydride and greater amount of benzyl bromide, then definitely you can have both products in which one of the hydroxyl group is protected, or the product in which both of the hydroxyl groups is protected, right? So it's important to use the concentration wisely. So you have to use lesser concentration of the reagent in this case. Again, we have another example. So here we have a diester, right? So you can see it is a geminal diester because both of the esters are attached to the same carbon here, and we want to carry out the monohydrolysis, means we want to hydrolyze only one of the esters, but we want to retain the other ester as well. So in that case, again, the reagent should be used in a lesser amount, right? So the reagent is sodium hydride in presence of methanol followed by the acid workup, right? But it's important that you use only one equivalent, means that you should use the lesser amount of reagent. But in case if you use greater amount of reagent, then the hydrolysis of the both of the esters will be carried out, right? So this is about the chemoselectivity in case if the two functional groups are present. Now we have chemoselectivity, right? And this is a reaction of a group twice when it can react once when it can react twice, right? So here we have an example, right? So we have an oxalyl chloride. So oxalyl chloride can react twice. How it can react twice? So for that purpose, you have to see its structure. So this is structure of oxalyl chloride, right? So oxalyl chloride is basically a acyl chloride of oxalic acid, right? So this is structure of oxalyl chloride, right? Here you can see that this benzyl alcohol can react with this, and also an other molecule of the benzyl chloride can attack on that. So this reagent, this oxalyl chloride, can act twice, but we only want to react once. For that purpose, what we use is that we use this reagent in a lesser amount. If you use this reagent in a lesser amount, then it will preferentially react only once with this oxalyl chloride. But in case if you are using this reagent in excess, then both of the chlorides of this oxalyl chloride will be displaced, right? So if in this case you have to use the concentration wisely, you have to use the concentration in a lesser amount. Now we have again two functional groups. So both of them are nitro group, but we only want to reduce one nitro group and we want to retain the other nitro group, right? For that purpose, for selective reduction of only one nitro group, what we use this NaSH, right? So we have to use the sodium thiol. So with this NaSH group in presence of methanol, this reagent can only reduce one of the nitro groups, while the next nitro group, the other nitro group, will not be affected, right? So that's all about the chemoselectivity. In the next lecture, we shall see about the chemospecificity. We shall also study about the regioselectivity, and we shall see about what do we mean by the stereoselectivity, right? So I hope you have understood this lecture well. Thank you for your attention.